Okay. Hello, everyone. Welcome to Learning at Lambert Labs session. And today's presenter is Tom. So over to Tom.
Yep, thanks, Aaron. So let me just share my screen. Okay, can everybody see that?
Yeah, I can see it.
Good. Okay. So what I have here is a circuit. If I look in the top left, I have an input of 4 bits, and I can toggle the input like that. So you can see the rail just below goes bold green, which means that there's current running through. And I can do that for each of these bits. And when I do that, you should see that this thing here displays the base 10 number. So that's 2 now, it's 0 now, but I can set it to 4. This is 8, and so on. I can pick any number between 0 and 9. So yeah, so that's the circuit, and what I'm going to do in this presentation is to show you how I built this. So that's my laser pointer. So so the first thing we're going to start with is the display itself. So if you look at the display, you can see it's got segments. It's actually got 7 of these segments. And basically, when we change the input, each of these segments will be either on or off, right? So either going to be 1 or 0. So the first thing that we can do is we can label these segments with lowercase letters. So A, B, C, D, E, F, and then we have G in the middle. So once we've done that, we're going to look at the inputs in more detail. So this table on the left shows the expected output for a certain input. So, we've got 4 bits. If they're all set to 0, then we see a 0. If there's 1, then we see a 1, and so on, up to 1001, which is 9. So we have these segments labeled. So what I'm going to do next is I'm going to rewrite this output in terms of these segments. And when I do that, you'll get this. So for example, if you pick 0, then all the segments should be on apart from the middle segment G. And indeed, that's kind of what we see. So A to F are 1, but G is 0, so it's off. And we just pick another example, like 3, for example, then we want E and F to be off. And you can see E and F is off, whereas the rest are on. So this is known as a truth table, and it basically tells us for a given input, what do we expect to see. And what I'm going to want to do next is I'm going to want to try to write a Boolean expression for each of these outputs, for each segment. And so we're going to start naturally, we're going to start with the A segment. Before we do that, just a quick reminder of Boolean notation. So in Python, we've all seen these keywords. We've seen and, or, and not. So in Boolean, we have a kind of direct equivalent. A and B in Python is A dot B. A or B is A plus B. And not A is A, but it's got a little kind of bar above it. So you can think of and as a kind of, this is basically a kind of multiplication sign, and the or is a sum sign, plus sign. So yeah, so once we've settled on that, let's have a look at the A output, and let's try and write an expression for this. So we want to essentially describe in which conditions is A 1 or is A true. That's another way of putting it. So we can see that for the case where the inputs are all 0, then A is true, A is 1. So what we can do is we can write A equals capital A, but we want not A and not B and not C and not D. The next row is 0, so we don't want to include this row, but we do want to include this row. So we add in another term, which is not A and not B and C and not D. Now we can keep going like this for all the other rows, but I'm already feeling a bit woozy, to be honest, because first of all, it's quite a bit of work, but also you can probably see that when we finish, we're going to end up with something that looks a lot like this table. Actually, it's not going to help us that much. But what we want is we want a Boolean expression, but we want we want it in the simplest possible. It expressed in the most simple way, with all the terms simplified and so on. So rather than write everything out and then try and figure out kind of by manually how to rewrite the expression, we're going to use something called KMaps to help us here. So what is a KMap? So a KMap is just a grid. And up here on the top axis, we put in the first 2 bits of the input. And here we have the last 2 bits of the input. Now notice how I've labeled each column here. So I have 0, 0, I have 0, 1, then I have 1, 1, and I have 1, 0. So 1, 1 is here. It's not at the end as you might expect. It's actually, there's a specific order that we need to follow, and it's very important that we do this. Otherwise, we don't really have a KMap. And I've done the same thing with CD as well. 0, 0, 0, 1, and 1, 1 is here, and we finish off with 1, 0. So each cell in this grid, it represents a row in this table. So this is just a table from before, but I've only included the A segment here. So if I take an example, let's say this first cell here, 0, 0, 0, 0, that represents this row here, etc. Now, what I do at this stage is I look at all the rows which have 1 as the output, and I write a 1 in the corresponding cells. So 0, 0, 0, 0 is a 1, so I put a 1 here. 0, 1, 1, 1, which is this cell here, 0, 1, 1, 1. You can find it here. It's a 1 as well. If there's a 0, then I just leave the cell empty. Like this is an example, 0, 1, 0, 0 is a 0. That's why I leave that cell empty. Now, some of these cells in this KMap aren't actually in the table. For example, this cell, 1, 1, 0, 0, it's not in the table, it's somewhere down here. So for all the cells which are in the KMap but are not in the table, I write an X like that. So that's the first kind of stage done. We've filled in the cells with 1s and X's. And now what we want to do is we want to group the 1s and X's together into rectangles. And the bigger the rectangle, the better. So I can already see a rectangle here, right here. So I'm going to draw a rectangle over that. And this rectangle covers all the cells which have one thing in common, which is that C is true on these cells here. All the other inputs, A, B, and D, they can change, but C is true. It has to be true for a cell to be in this rectangle. And so we can write in our expression, we can write A equals big C. And that's our first term of the expression. I can see another rectangle over here. And it's fine if rectangles overlap, that's perfectly okay. So I'm going to draw the rectangle. And this rectangle represents the A cells, because A is true for all these cells. We got 2 1s left, so we need to cover those. So I can see I can see a square here, which is, I guess, a kind of rectangle. So if I draw that, so this square represents the cells where B is true and D is true. And you can check that for yourself. B is 1 for these cells, and also D is 1 for these cells. Now we've got 1 cell left to cover. And what we could do is we could just draw a rectangle just on the cell itself. But remember what I said at the beginning, that the bigger the rectangle, the better. So instead, I'm going to draw this. And what I've done actually is I've drawn a square here, but the square sort of goes over the edges, and I've sort of drawn it back here and here and here. And I can do that because these cells in the corners are either 1 or X. So I could draw the square here. And this square represents the cells where B is 0 and D is 0. And again, you can check that for yourself. And that's it. And that's actually our final expression for A. And that's, I think, much better than what we were doing previously, where we were going row by row. So yeah, so this is our KMap here. This is the expression we just derived. And this is the original truth table. And we can, before moving on, we can just do a very quick sanity check that this makes sense. So remember, we wanted an expression which gave us the cases where A is 1. So this expression tells us that A should be 1 when C is 1. So is that true? Well, C is 1 here, so A is 1. C is 1 here, so A is 1. C is 1 here, A is 1. C is 1 here, and A is 1. And when that's fine. So that kind of shows that this term makes sense, and we can do the same for all the other terms. I'm not going to in this presentation, but if you want to, I'll put the link to this presentation later on, and you can check for yourself that these make sense, basically. And so once I've done this for A, once I've gotten the expression for A using a KMap, I'm just going to do the same for all the other segments. And this is what I get. And so this here on the left gives us all the information we need to tell us whether a segment will be on or off for a particular input. And remember, that's capital A to capital D, that those 4 letters, A, B, C, and D, they represent the input. And so yeah, so this just does give us all the information we need. So this is all well and good, but how do we turn this into a circuit? So in circuit design, we have some logic gates that we can use. And logic gates basically map directly to Boolean operators. So in this case, we have A and B. And the logic gate for that is this symbol here. And so if we send in a 1 and a 0 to this, we'll get a 0 in Q. Or if we send 2 1s, then we'll get a 1. This is what an OR gate looks like. So here, if I put in 1 and a 0, I will get a 1. Only when I put 0 and 0 will I get a 0. Otherwise, I'll get a 1 in all cases. And finally, we have the NOT gate, which just takes the input and inverts it. So here I send in a 1, I'll get a 0. If I send in a 0, I'll get a 1. So to build the circuit, what we first need is we need basically these inputs. We need rails for these inputs. So here I've got 4 inputs here. So I've got A, B, C, and D. And what I've done is I've also created an additional rail for each of these inputs. And I've inverted the input to give the complement. And this is why we have A and not A, B and not B, and so on. So I've actually got a total of 8 rails here. And then what we do is we create a kind of, we write each of these terms in terms of logic gates. So when we have a C, then we just draw a link to the C rail. We have an A, we draw a link to the A rail. B and D, we take the B rail and the D rail and we send it through an AND gate and we get a B and D. And not B and not D is pretty much the same. We just take the not B and not D rail. And then to get the actual A, we just OR all these 4 together. So this is pretty much just one big OR gate, but with 4 inputs. And this is the result, and this is the equivalence to A. So here we're going to get A. And that's pretty much it. That's how you create the circuit for the A output. And what I've actually done, so that's a link to the circuit. And if you look at the circuit again, so I've done that same procedure that we just did for A. I've done that for all the other segments. So this is A here, but this is B, C, D, E, F, and G. So I've done that 7 times, basically. It's the same process. I've taken those 7 expressions and I've turned them into circuits. And then each output I just send to the correct circuit, to the correct segment. So the A segment was the top segment. So you can see this wire here goes to the A segment. And the G segment was the middle segment, and that's connected to this last, I guess, yeah, part of the circuit. And you can see again how this works. That's a 9. If I go above 9, then the behavior is actually undefined because we didn't include that input in our table. So we actually have no idea what's going to happen. So for intents and purposes, we're limited to 1100 as our kind of top. In fact, 1001 is 9. So just 1100 happens to show a 9. But actually 1001 is the top input. So yeah, so that's how to design a digit display. So yeah, that's the end of my presentation. I'm welcome for any questions.
Thanks, Tom. That was that's amazing. So yeah, sure. I'll open the floor to any questions, really.
So Tom, I mean, during the interview, you spoke about KMaps, and you gave me a nice insight into how they work. Now, one of the things that I don't know anything about, but I have heard about is kind of k-means clustering, and I'm sure there are plenty of other pieces of terminology that I don't understand with the letter K in it, if you like. Do you know how to extend this kind of basic signal demonstration into wider uses, if you like?
Well, I'm not actually familiar with other, well, so I've used a KMap in this presentation. KMap, this K stands for, I think you pronounce it Karnaugh. It's a surname of the person who designed this method. So the only thing I can really say in terms of that is that you can extend this to higher bits. So you can have 5 bits, 6 bits, and so on. And you just kind of, if we had 5 bits inputs, then you would of course put in, if you have maybe A, B, C up here and then D, E down here, and you just have kind of the KMap would extend across here. I mean, nowadays, I suppose K-maps aren't used that much because we have computers to simplify these Boolean expressions for us. But obviously, the person who was building the first computer, they didn't have the computer to help them build the computer. So at some point, K-maps were necessary, or helpful at least. But yeah, I mean, yeah, I don't really. I haven't actually read about kind of other uses of K in electronics. So
Could be completely unrelated. I just didn't know if you knew about it. Hey, there we go.
yeah, I'm not sure. Yeah, I think this is a special K. Like this is just this stands for Karnaugh, and people just shorten it to K. But yeah, I guess there are other uses of K in electronics. Yeah.
I've got a question, Tom, actually.
Yeah.
Like, what would you say is the best way to control that undefined behavior when you start reaching 10, 11, 12? Because I guess off the top of my head, would you be using some kind of multiplexer to try and select the power on and power off for the whole LED array? If you got to like undefined bits, or is there a more kind of a less verbose way of doing it?
Well, maybe there is. I'm not actually sure about that. Because at the moment, anyone could just put in any input and they'll get they won't get the right answer. So yes, I'm sure there is a technique to use. I wouldn't know off the top of my head how to control for that. The only thing I'd say is that probably what most people do actually in this case is they extend this to all 16 inputs, and then they update this table to handle the letter A, B, C, D, E, F, because you can do that on this digit display as well. And that's one way of getting around it. It's probably the most efficient way, really. But yeah, in general, how to handle don't cares. I mean, there are various ways. Yeah.
Cool. Does anybody else have any more questions they'd like to ask Tom? Okay. Well, thank you once again, Tom. And yeah, thanks everyone.
Yeah, thanks everyone.
Thank you, Tom.
Thanks, Tom.
Cheers, Tom. Thanks. Bye.
Okay, I've